So the next talk will be by Edoardo. I hope I pronounced it correctly. Edoardo? Yeah, okay. And Edoardo originally studied physics and somehow morphed into a software engineer, right? And you love both coding and mountains, which is a perfect match for the Swiss Python Summit. And yeah. Who of you knows Advent of Code, like the puzzle thing is? I think Edoardo will give you some nice improvements how to make it not only functional and working, but also elegant by using itertools. So yeah, thank you a lot and welcome, Edoardo.
Thank you. Thank you.
Thank you.
Okay, thank you, Rafael, for the nice introduction. And I'm very excited to be here on the stage today. I've been at many Python conferences now, but this is my very first time I'm on a stage talking about something like this. So I'm doubly excited today. So I know it's just after lunch, so I'm sorry, but I'm convinced that I'm going to talk to you about something fun, at least. But I really hope that you are going to take some bits away, home, this tonight, whatever, that are going to make your Python more useful and actually maybe more efficient. So I'm a physicist by trade, but I now work as a research software engineer at the Swiss Federal Labs of Material Science and Technology. And I like to call myself a computer science wannabe because probably in a parallel universe I studied computer science. And my very first language I learned before high school was the Wolfram language. I don't know how many of you here knows the Mathematica, the symbolic software, but obviously I quickly fell in love with Python. And currently, I'm having a crush for Rust, and you know why. Maybe you heard about this language. But let me just do a disclaimer. I'm not a competitive programmer, and I'm actually quite slow at coding sometimes, so I don't count Claude, ChatGPT as cheater, obviously, at least in this context. But I do find fascinating trying to explain to a machine how to solve puzzles or problems that our human brains find sometimes even easy. So let me just, actually, Rafael spoiled the question, but how many of you knows about Advent of Code? So just raise your hand. Okay, good, man, nice. How many of you tried at least once or twice? Okay, every year, so you can take my place now. No, every year, you did it every year. Okay, no, okay, sorry. Okay, otherwise we need to have a chat. So what I want to share with you today is how, through Advent of Code, I learned to think in data transformations instead of step-by-step instructions, and what we may call an imperative approach. And we will see together a couple of example puzzles, and we will discover some gems that are, for me, that are hide in plain sight in Python standard library. So whoever of you tried at least one puzzle of Advent of Code, I'm pretty sure you are familiar with this pattern, like this triply nested loop, then we have some checks, then maybe, I don't know, we have a grid problem and we need to check something for neighbors and so on. And then maybe even the doom of nesting continues here, no? Because this is like what we may call a brute force solution. This is somewhat typical, okay, in an Advent of Code puzzles. But what if I tell you that most of the time you can write something like that, which is almost, I'm not saying it's identical, but almost similar and provides the same result. Is it better? Well, that's not quite the right question. I think, both approaches are correct. They work, they deliver the correct result, as long as you type correctly, obviously. But only one describes the solution, meaning what you want to do versus how you do it. So this is what we call a functional approach. So we have to talk about what's functional programming here. So I'm not going to dwell too much deep because it's like a topic that will take an entire textbook or university classes, whatever. There are many definitions that change depending on the language you're using also, but we will use a simple one. It means working with functions, obviously, over streams of data. And functional programming actually rests on a few principles, and I'm going to explore these three mainly. Okay, let's focus on the first two, pure function and immutability, which are tightly coupled. Pure functions Pure functions mean that obviously functional programming is all about functions, okay? So our inputs flows through function and then we can chain them. One output can become the input on another function, okay? So pure in this context means that there are no side effects. So no printing, no file I/O, modifying global state, this is strictly forbidden. Purity means this thing. And then we have the concept of deterministic function, meaning that if we feed the function with one input, with the same input, we always guarantee to get the same output. No question, no exception here. Immutable data, on the other hand, means that data structure can be changed after they are created. Pretty much like, immutability in Rust. No, when you create something, it's there. By default, it's immutable. You cannot change it. If you need to change something, you need to create a new version of the data, okay? Obviously, they work together because if your data can change, it's much easier to write pure functions because no mutations almost always means no hidden side effects. So let's look at a principle, an example in action. I think that many people, if you work with neural networks, you know what I'm talking about. This is like the simplest activation function that we maybe use in classes when we learn what neural networks are. This is just a simple function that takes negative and drops them to 0 and positive values remain the same. What's the most straightforward way we could write this? Implement the blue, okay, the blue function. Well, we could write something like that, okay? Capitalize. Typo. So we could write something like that. So we have an array, and then we loop over the array, we keep the index, and then we change the value in place of that index with the max between the value itself and 0. Looks reasonable, no? Then we iterate the other array, and then we return it. Good. But if we try to use that function, what happened to our data? We kind of lost our data. Now you see that the result and the data we feed are now the same, which we are violating the very first principle of functional programming, okay? So this is a side effect. The function reads outside and modified, change something from the caller's scope, we may say. How can we do it? Well, we can say, okay, we are not modifying data and we are returning a kind of a new copy of data. And note that here, I also wanted to stress that I changed the type and I'm returning a tuple to kind of enforce the fact that immutability, okay? Tuples in Python are immutable, okay? Take home message here is that pure functions are predictable, testable, and mostly safe to use anywhere, okay? The third principle I listed before was the functional programming rests on the concept of higher order functions. And I'm pretty sure that everybody here knows the sentence that functions are first-class citizens in Python, which means that functional programming requires that function can take other functions as input, and they may return function, which we can then pass to other function and so on. So I would think that the prime example is the concept of decorator in Python, no? Something that can modify the function, the behavior of an arbitrary function by chaining this, getting a function as input and returning another function. But there are also other things in the standard library that follows the same principle. For example, the operator module provides us with some functional equivalent of many operator like the plus, minus, and also the accessor operator by which we can access, an attribute like name or even complex nested attribute. Because as we know, another thing, in Python, everything is an object, so you can use the attribute operator, the accessor operator pretty much on anything. Then the last thing I want to revise before jumping in the calendar is another two concepts that are central to functional programming. And these are iterators and generators. And we have both of them in Python. So in short, an iterator is a stream of data from which we can get one element at a time. So we use the next language keyword to ask for one element. And we have to remember that iterators are consumed, so they can be exhausted. Once that happens, they are gone forever. We have to rebuild a new one. And this happens when the code itself will raise the stop iteration exception. On the other hand, generators are, we can say, if a function returns a value, then generator yields a value. The important point here is that some of the things I'm going to show you later, all of these functions are returning iterators. So we can say that generators are an handy way to create values on the fly, and obviously they return something that behaves like an iterator, by which we can call next, they are exhausted, and so on. Just one note, I mean, here, what we say, we hear often that generators and also iterator are so-called lazy objects. And what does it mean here? Maybe I'm saying something obvious, but let me clarify. What does it mean lazy here? So in the first example here, we are building a generator expression where we kind of prepare a sequence of squares from 0 to 1,000,000, okay? But we technically don't build that stuff. We just keep them in a special place, and when we need them, we can get one element at a time. The second example, and this is what we call lazy, because it's memory efficient, doesn't consume anything until we need the element that we want to operate on. On the other, I mean, the second example is that we have just a list comprehension, so we are building, literally building in memory all the number from 0 to 1,000,000. Okay. So what we call this eager expression. Again, the modules itertools almost always return iterators. So this is a nice, I mean, we need to remember what we are dealing with. The function itself, without even import statements, Python provides us with built-ins that are, I would say, the building blocks of functional programming. Like, for example, map to apply a function to an iterable, or even a function with multiple arguments to pair triplets or tuples of arguments from, like an infinite sequence of iterable. Then we have filter, then we have the zip, which is magical for me. Enumerate, anybody knows. All and any are like, they just return Boolean, so this is an exception. They are used in functional programming, but they don't return an iterator. They just return true or false according to a predicate. So let me say a few words about map and zip, if you don't know them. Again, map just because we are going to find them later in some examples. So map, again, applies a function to every item of an iterable and returns, again, an iterator. So we have to print it, we need to convert it to a list. And zip essentially pairs corresponding elements of a sequence of iterables. The first one that the shortest one, when one gets exhausted, then everything stops. Okay, now let's jump finally into the most fun advent calendar, and I will show you some of the most common patterns that you will encounter during your journey until Christmas. So the first one is about sequences and neighbors. So the type of problem that these problems are usually asking us to relationship within adjacent elements. They can be simple arrays, or they can even be multidimensional grids. So in particular, if we take the problem number 2 of last year, actually, so we have a series of sequence of integers, and we have to decide if a sequence is safe or not safe by following these 2 rules. So the differences between adjacent, again, elements must be of the same sign, and the difference must be between 1 and 3. So the difference cannot be greater than 3 or less than 1. So the first sequence, for example, is just taken from the calendar, is considered safe, but the second one is not, because there is a jump from 2 to 7. And then also the third one is not safe because there is a jump from 6 to 2. Okay, so what can we do? Let's figure out an imperative approach. The core part is actually the first 6 lines, where we build a container, a list, and then with this, I would say, quite readable syntax, but we build the difference between one element and the next one. And then we use we already use like the all key, like the all function to check if all the differences are greater than 0 or less than 0. And then we are again using all with the generator expression inside to check if the absolute value of the difference is within bounds. Okay, so pretty clear, but we can do, I think, better. And here is where we reach out for the first trick, kind of. So we can, is the right slide? No. So, okay, so we can import this function called pairwise from the itertools modules, and pairwise does what you think it does. You feed an iterable and it will return pairs. You see overlapping pairs of element. So you can see why. So when you see consecutive and adjacent, think pairwise. So here, the functional approach is pretty much similar, but definitely, I would say, clearer and also, fewer lines of code. So we use pairwise to build from our repo the sequence of differences, and then pretty much we do the same thing. No? We check the sign, we check the magnitude, and then we return if both conditions are satisfied. So this produces the same result as the imperative again, but I believe that this really focuses on what we want to do instead of how, like building the list and filling it up. So another common pattern is with products and combinations. So pairwise handles the case where we have pairs, but what if the problem asks us to try every possible combination? Okay, so that's when we need a different tool. And for example, the seventh day of last year, called bridge repair, was giving us like a numeric arithmetic expressions without the operators, and then the final result. And so we were asked to essentially insert in how many ways we could insert the operators plus and product times in between the numbers to obtain the final result. Okay, and remember, here a note, operators are always evaluated left to right. No precedence rule that we learn in primary school. So for example, the second sequence here can be obtained in two ways, either with 81 plus 40 times 27, or even you could swap the times and plus, and you would get the same result. So let me show how, actually this is not my solution, but a friend's imperative approach, which is super elegant, but I think hides what we want to do inside an obscure construction. Here he essentially tries all the possible combinations. So if we have k numbers, we have k minus 1 slots for the operators, right? And so we have 2 to the power of k minus 1 possible combination of all the operators that we have. So here we are building the results step by step, and then he's using an obscure, at least to me, bitwise manipulation to choose if we need to pick like the sum or the product operator. So it's fancy, it's elegant, because to be honest, it is elegant, but it's, I don't know, I don't find it clear. And again, we have bit manipulation, we have manual loop mechanics, and even if it's compact, I don't get immediately what he wants to do. So here is another function that we can borrow from itertools, which is product. So product, again, build the Cartesian product of either two sequences, or we can even build a Cartesian product with a sequence with itself, and we can specify with the repeat keyword argument how many times we want. And in particular, for our day 7, what we need, essentially, is the product of all the possible operators, given that the number of operators can be quite large. It's not only 2, maybe we have 10 slots. So you see already where we are going here, no? So with 3 numbers, we need 2 operators that should, so 4 combination, and products, operators with a repeat equal to 2, which is the default, generates all of them. So let's approach it in a functional way. Well, okay, I mean, it's also more compact, but I still find it, I find it even clearer, because what we are doing is we are building all the possible combination of operators. Then again, we are starting from the first number, and then we are applying in a functional way, because here OP is the operator itself is either add or plus that we imported from the operator module. And then the test is the same. But to me, this is 10 times clearer because, again, we are focusing on what we want to do. Keep in mind that I'm not saying that this functional approach, which, yeah, it's clearer, is the best in terms of execution time. So, okay, maybe it's not even the most efficient sometimes, but might not be the best. I mean, might take maybe the same time as the other. Okay, but we are not like here fighting about the fastest coder here, especially not if you want to get into the leaderboard of Advanced Code, which is impossible. But then itertools has many more tools that you can reach out. And for example, we have everything that deals with combinatorics like combination or permutations, and also combination with replacements. And many Advanced Code problems ask you to deal with the combination or permutation, like, I don't know, graph path enumerations, or find ways to distribute these items in these slots, and so on. There is a third and part that I want to share with you, which is about aggregation and reduction. So we have seen how to generate combination with the product. Now the question can be, how do we combine results across a collection? So how do we collapse data into a single answer in a functional way? So here we have like two, so combining values across collection. Here we have two complementary techniques, which are pretty standard math or like linear algebra operation, which is transposition. And we are going to use our friend zip. And then we have the reduction operation. So let me, again, go to one of the, back in time a bit, 2021, day 3. We have this problem where we have a long list. This is just an example. It's not the whole input. We have a long list of a sequence of 0 and 1. And then we need to find what are the most and least common bits in each column of this input. Imagine that the real input is like maybe, I don't know, 10,000 lines. And the width or the number of bits in a sequence can be even, I don't remember, maybe 50 bits, something like that. So what would be our imperative approach? That's actually what I wrote for this solution. Again, I started building the string because the puzzle was asking us the binary form, so I built the string and then converted, but this is irrelevant here. The thing is, I'm again building from the beginning, from an empty string, and then I'm looping over for each row of data, actually for each column, and then for range in columns, then for each row of data, and then I'm checking if the column is 0, then I'm incrementing the zeros counter, otherwise I'm doing with the ones, and then I'm checking if ones are greater than zeros, then again, keep track with 1 or 0, and then I can return the result. Here, our friend zip, combined with the so-called unpacking operator, simplifies this a lot. Again, zip returns an iterator. So we can combine with the star, so the unpacking operator, in one line, without building an intermediate container, to transpose our data. Okay, so we have, again, this is just taken from the example. From that array, we can get literally the transposed object of this list of lists. Okay. Again, zip then pairs up the first element of the first iterable with the first element of the second iterable, and so on. That's why it works combined with the star operator. So we have the columns, and how can then we write in a more functional way? We can first define a function that actually compute the most common bit, which again checks with a generator expression there. If it's 1 or 0, you can do it in probably other ways, but that's not the core part. And then we are combining both the zip star trick to transpose our metrics and the map built in to apply our most common function to every column now, because we have the opposite. No? We have transposed rows to columns, and then we process each column. Again, I find it, much more readable than the other. Again, even if both they are producing the same exact correct solution. So now we have a collection of bits, 1 per column, and we need to build a single binary string. So that's where the reduction comes in. So we are folding multiple values into one. And again, Python, and in particular the functools module, has the thing for us, which is called reduce. So what reduce does, you can imagine, it just folds the list into a single value. In this case, we start with the first element 1, and then we apply the function plus, accumulating the intermediate result, and keep adding the next element to the accumulator. Okay, the final result in this case is 15. And fun fact, the reduce never became part of the standard library because apparently in 2005, I think, Guido Verrossum said that he always needed to grab pen and paper to find out what reduce was doing, except in simple cases. So that's why reduce is relegated to functools and never became like zip or map part of the standard library. So how can we revise the first, so the day 3 with the reduce? I admit that this is a bit maybe overkill because we could just join string with the join built-in, right? But this is just for showing everything in a single solution. So most common bit is the same function we defined before, and then we find what are the most common bit, and then we reduce the result with add. In this case, add is just the concatenation between strings. Okay, so we can also have more complex operator like, I don't know, multiply all numbers or merge dictionaries or min max with some custom logic, and where reduce becomes much more powerful than a simple concatenation of strings. Obviously, this is not all. This is just a table I put together with some of the, I think, the most useful itertools function that you can find built in, again, where you have permutation, combination, and so on. The zip data is actually not in itertools, but yes. So, and if you want more, people thought that itertools was not enough. So there is a package called more itertools, and you can get like other iterators for example, for Windows, which is very useful for advent of code. I find it, I used it at least a couple of times. And then we have chunked if we have, again, if we want to split the, similar to pairwise, or even flatten to like unravel a sequence of iterables in one single list, okay? They are especially useful. But let me also close with one example where I try to convince you that going functional is not always the right way. Because, for example, in this puzzle, again from last year, the integer sequence was like an alternate, was a disk representation kind of. So we had like an alternation between the length of a file and the length of a block of free spaces. So, and the goal was to compact the disk to move the blocks until no gaps, okay, of free space were there. So the first compact format becomes the second if we expand, where the dots are the free spaces. So you think that here we have to track a mutable state of the disk, the current disk layout, and then we have each move operation which modifies the states. So we have many of these state changes. Trying to copy in a functional way the data every time, you can understand that this gives you a terrible performance and memory usage. So this was actually my solution, a part of a snippet. And here, I would think that there is no escape from a mutable or imperative, non-functional approach. We need to track the state of the system, and creating a class is by far the easiest. Actually, would produce the most clear code. Okay, so code clarity beats sometimes cleverness or smartness, because remember that explicit is better than implicit, right? So functional doesn't mean dogmatic. We should use the right tool for the right job. So again, last thing I want to just recap. What are the takeaways from this? Especially for a coding challenge like Advent of Code, I think that thinking in data transformations and not steps gives you a better insight in what you want to do versus how you are achieving that. Remember that itertools and iterators, generators as well, are your friends. Sometimes thinking in math combinatorics is much better, beats nested loops, and then choose the right tool for what you have to do. Advent of Code puzzles allows many different approaches, but some of them are clearly better than others in some puzzles. So here are some, I mean, it's a shamefully incomplete sample of the enormous amount of resources that are out there that you can find about functional programming applied to this. So like, I will publish the slide obviously so you can get these, take a picture if you want. But there are many, many more. Just run your search and you will find these and many more. So I know we are more than 2 months away from Christmas, but I don't see a better occasion to wish you all a Merry Functional Christmas. And I'm more than happy to engage in any discussion later if you want to talk about these seemingly useless puzzles that will occupy your 25 days to Christmas. Thank you.
Thank you. All right. I don't think we have time for questions, but they can reach out to you in the break.
Absolutely,
right?
absolutely.